Welcome back to the playlist on UV-Vis Spectroscopy. Alright, so in this video we're going to go over the theory of UV-Vis spectroscopy and why you would ever want to use this. But in order to know when you would ever use this technique, you have to know how it works. Alright, now over here on the right side of the screen, alright, I have several very different molecules. Notice some of them, like this one right here, this is butane. 4 carbons long, and it has no double bonds. It's completely saturated. Right here I have this is actually referred to as transbutene. Okay, it has 1 double bond here, and then I actually have a conjugated diene right here. This has 2 double bonds, and they are conjugated to one another. And then some of these other compounds, like this one, is a triene, and all 3 double bonds are conjugated. This one actually is a little bit different. It has a nitrogen thrown in there in a lone pair, but all of these pi electrons, and it's key that I said they were pi electrons, they are conjugated. This is an aromatic molecule. This is benzene. All right, and then this is certainly a very conjugated molecule. This is a biological molecule called heme B, and we're just going to see some others, okay? And the reason I show you all these molecules is each one of these is going to have very different absorption properties, meaning that they're going to have different capacities to absorb UV light at various wavelengths. All right, one really important thing when you're using specifically UV-Vis spectroscopy is any molecule, for the most part, that does not have a double bond in it, we don't even consider. All right, so if you, for whatever reason, wanted to measure butane, just simple butane, completely saturated, UV-Vis spectroscopy is not the way to go. It has no double bond in it, okay? And so if you want to measure butane, you're probably going to want to use something, if you think you have butane, like mass spec. All right, mass spec, NMR are going to be a lot better choices if you want to quantify or at least qualify that you have that. So that pretty much leaves anything else to things that have double bonds. Now, if you notice this molecule right here, this one which is just transbutene, this one has a double bond. And theoretically, this one actually can absorb light. Specifically, it'll absorb more in the UV range, okay, not the visible range, but it does have some absorption properties. Now, even when we're talking about molecules with 1 double bond, it turns out that their absorption patterns, when there's 1 double bond not conjugated to anything else, they're also pretty weak usually. So ordinarily, we really don't even consider these either. A much better choice to quantify this would also be NMR and mass spec, okay, which are not in this playlist. However, it changes a little bit when we talk about molecules that have more than 1 double bond, and those double bonds happen to be conjugated, all right? So conjugated essentially means, if you want to check to see that 2 double bonds are conjugated, it means that the double bond is separated from another double bond just by a simple sigma bond, or a single bond. Okay, so you just see a double, single, double, and then potentially single, double, and so forth. Very much like you see in this one. This one down here is single, double, single, double, single, double. And if you have a series of double bonds and they follow this sort of pattern, they're conjugated. Okay, so something like this diene that's conjugated, or this conjugated triene, would actually have some usable patterns of absorbance for UV-Vis spectroscopy. Okay, another one that could also have useful ones is this compound right here. So I have a double bond there, a single bond. Now, even though this is a nitrogen, this double bond still is conjugated to this double bond. And then I have single bond, double bond, single bond. I also have a lone pair here, but that's also counted as part of the conjugation. Okay, now to keep that lone pair there, you probably have to have a buffer in the system. Okay, but still, this lone pair and these 3 double bonds are conjugated to each other. So this would also have some useful, it would have a wavelength of absorption in the UV spectrum. Okay, this is benzene. Benzene also has an absorbance in the UV spectrum. Okay, that's pretty useful. All right, this molecule right here, this is heme B. And normally when you talk about heme B, which is a biological molecule, and this molecule is very useful for detecting proteins that have heme in them, because generally the wavelength of absorption is approximately 450 nanometers, which happens to be in the visible range, and we'll talk about the implications of why this would happen to be in the visible range. Okay? Now, having these conjugated double bonds, and if there's a lone pair that's conjugated, which adds to the conjugation, that's also useful to be able to see that. But there are also some other things in molecules that tend to also produce a little bit of UV-Vis absorption, although these are not as useful. These right here, these double bonds, they're just double bonds, and we're specifically talking about the pi electrons. Because remember, every double bond has 2 sigma electrons and 2 pi electrons. We're only concerned about the pi electrons, all right? But there's another type of electron that can also produce some less than usable data in some of these analyses. And those are these non-bonding electrons. And generally the non-bonding electrons, we're just considering lone pairs that are not tied up in any kind of resonance or conjugation. Okay, so these 2 lone pairs, these 2 right here, these would essentially be non-bonding. And whenever we're talking about non-bonding electrons, generally for UV-Vis spectroscopy, we give them a symbol N. Excuse me, I'm a little bit under the weather. Whenever you see an N in UV-Vis spectroscopy, that's generally referring to a non-bonding electron. If I'm talking about any of these pi electrons right here, generally I'm going to give those just a pi. And notice, again, it's not sigma that we're concerned with, it's pi. Now, out of these 2, the more useful signal by far are the pi electrons, okay? So we're really going to be concerned mostly about pi electrons, although you can get signals for non-bonding electrons, okay? So that's just a general idea of what kind of molecules you would want to scan using UV-Vis, all right? All right, now it's time to go into a little bit more of the technique itself, okay? So one key thing is, and there's different ranges for this, but they're all approximately the same. If you have a wavelength between 190 and 380 nanometers, that's what we call the ultraviolet range. Okay, this is the UV part of what we'd be measuring. And if we have any wavelength between 380 and 750 nanometers, this would be the visible part. So when we take wavelengths from 190 to about 750, sometimes it can go up to about 800. But this, in general, this would be approximately the UV-Vis region of the spectrum. This is where all of these molecules that I talked about were important. They're all going to be somewhere in that wavelength range. Okay, but what kind of signals are really useful for us? Okay, well, remember what I talked about. We're not concerned with sigma bonds, okay, and sigma electrons. So this first thing right here, where we have the sigma going to sigma star. Okay, what does that even mean? Well, essentially what's going to happen, and we'll talk more about the actual technique in the next video, but when you do a UV-Vis spectroscopy, okay, say I have some compound. Let's say I have this compound. So something, it's conjugated, right? Something like this, all right? What I'm going to do is I'm going to have something in the machine that's a light source, okay? And of course, we probably know this by now, but your sample of this compound is going to be in what's referred to as a cuvette, okay? It's usually about 1 centimeter long, okay? And you're going to have a bunch of this molecule at some concentration in a solution inside this cuvette. The machine is going to use the light source and shine some light at this sample, okay? Some of the light is going to get absorbed by these molecules in here. Okay, some of it will actually go through and not get absorbed, but a portion, some percentage of this light from the light source, okay, is going to get absorbed by this molecule, okay? And the 2 main types of electrons that are really good at absorbing this light happen to be pi electrons and non-bonding electrons. These are the 2 types of electrons that tend to absorb that light, okay? And so basically, whenever those electrons absorb the light, they get excited. Whenever an electron gets excited, that generally means it's going into a higher energy state, okay? So the electron was at some energy at rest. When it absorbs light, it goes up in energy for a little bit, all right? So in this case, I have this sigma electron. It absorbs some light and then goes into sigma star. Okay, when you see this little asterisk or this star after the symbol sigma, that means that this is the excited state. So we're talking about this is the excited state, and this is the rest state of that sigma electron. Now, again, this type of absorption is not really that useful for us because the signal tends to be pretty weak, all right, for sigma transitions. So when we transition from sigma at rest to sigma star or sigma excited, that's not very useful. These two over here are actually both more useful than this one. And by far the most useful one is this pi to pi star. So the nomenclature actually means the same thing, except we're talking about a pi electron. So you shine light on, say, any of these compounds here. So maybe we shine light on this conjugated triene. And the pi electrons, the pi electrons absorb that light, and those pi electrons go into an excited state. All right? And that state is this pi star that you see right there. Okay? And whenever we are exciting it, notice that on the vertical axis here, this is energy. All right? So we start off at this energy, right? So this energy right here, this is what we start off with. And then we ultimately end up at this energy up here, right? So in other words, what I have here is a difference in energy, right? I have a difference in energy, and normally the way we quantify that is we call it a delta E, a change in energy, okay? It turns out that this change in energy is actually equal to something that you probably saw in general chemistry. This delta E is equal to Planck's constant, which turns out to be 6.626 times 10 to the negative 34th joule seconds, times the speed of light divided by the wavelength of light. Okay? So if you were ever able to know this delta E, and you know Planck's constant and the speed of light, because those two things are constants, you can calculate the wavelength of absorption, which is a really, really useful thing. Okay? And it turns out that different energy gaps correspond to different wavelengths. Okay? Now, one thing you can actually see is that the E here, the energy and the wavelength, are inversely proportional. So one very important relationship is as the difference in energy actually goes up, that corresponds to a lower wavelength. All right? So it turns out that higher energy things, higher energy molecules, tend to absorb at lower wavelengths. And then if we have low energy molecules, they tend to absorb at higher wavelengths, okay? So it turns out, and we'll talk about more why this is in another video, but lower energy molecules, they actually are ones that usually have a lot more conjugation, okay? They sometimes tend to be aromatic, they are, but in most cases they just have a significant amount of conjugation. They will tend to absorb at higher wavelengths than something that just has two conjugated double bonds. Okay, so but that's just one of the relationships that comes out of this. Then the other transition that we can have is N to pi star. Okay, this is when we have a non-bonding electron. It absorbs some light from the light source of the spectrophotometer and goes up in energy to the pi star state. This one is not as strong of a signal, so it's generally not as useful to us. So generally what we're usually measuring, it turns out, is actually this transition from pi to pi star, okay? And the reason that this is not something you usually need to know, but actually the reason why this N to pi star is actually not as strong of a signal is because the non-bonding electron in its orbital actually has a different symmetry than the pi star. Pi and pi star actually have the same symmetry, and so the transition is a lot easier for that. We normally consider N to pi star a forbidden transition, but it actually can occur. But that's why pi to pi star is actually a much more usable signal, and it's actually a stronger signal. Okay? All right. So this is just a very general kind of range of wavelengths where you find typical transitions. Okay? If you have a pi to pi star transition for an isolated double bond, that could actually be something like this compound right there. That's an isolated double bond. The absorption tends to be very low in the UV range, okay, around 200 nanometers, all right? That's actually not a very strong signal. But if we actually move to pi to pi star for a conjugated diene, or if we have a large amount of conjugation for pi to pi star, you can see that the wavelength of absorption actually goes up. It's much higher than if it's isolated, right? And if you have a lot of conjugation, you can actually get the wavelength up really far. Also, these two signals right here tend to be pretty strong, Okay, and actually, the more conjugation you have, you also get pretty strong signals too. Um, N to pi star occur at higher wavelengths than pi to pi star generally, okay, but they're not as useful. There are cases where you may have to use them, and that's sometimes whenever you have overlapping signals. If there's two molecules in a solution that absorb at the same wavelength, sometimes you have to default to these. But if that's not the case and you're just measuring one thing, generally you're just looking at the pi to pi star signal, and it's usually a larger signal than N to pi star. Okay? And so this is kind of the basic theory of UV-Vis spectroscopy, all right? We're going to shine light in the UV or visible wavelength at a sample in a cuvette. Some of these electrons, only pi and non-bonding electrons for the most part, are going to absorb that light. And those electrons are going to go up in energy, as you see here. And the pi will go up to a pi star state, meaning an excited state, and the N will go up to a pi star state, okay? And just remember that the difference in energy between those two states, okay, is equal to hc divided by the wavelength. And so that generally means that as you increase the energy, the wavelength of absorption goes down. As that energy gap decreases, the wavelength tends to go up. All right? And so that is the basic theory of UV-Vis spectroscopy. Now, in future videos, what we're actually going to do is we're going to actually go over how you calculate a theoretical wavelength of absorption. It turns out there are some rules called Woodward-Fieser rules that allow you to actually calculate a theoretical wavelength of absorption, so you know approximately where to test if you don't know where the wavelength is. Now, nowadays you can Google it, but if you have a novel compound and you're trying to see where it absorbed, you can actually calculate approximately where that should be. Okay. We're also going to go over how you actually deal with the data, because you can get different data from this type of experiment. And from that, you can determine unknown concentrations. One of the last things we'll do is we'll talk about how you can actually measure the rate of a reaction. That's very useful for biochemistry because many biological reactions produce products or consume reactants that tend to absorb in the UV-Vis range. Okay? So, and it can also be useful for identifying proteins. If you have a protein that has a specific coenzyme in it, like this heme B, and that coenzyme absorbs, then you can also use that. If your enzyme doesn't, or protein doesn't actually have a coenzyme, sometimes there's amino acid residues in the protein, like tyrosine, tryptophan, and phenylalanine, that absorb at wavelengths in the UV-Vis region, and you can detect the proteins that way. Also, and so it's very useful. Also, one of the things that you can do is if you're measuring DNA or RNA, DNA has a specific wavelength of absorption in this range. RNA has a different wavelength of absorption that's also in this range. And so you can identify DNA and RNA in a sample and see how much you have. All right? So this is the general theory. In other videos, we're going to work upon how you deal with getting data, producing it, and analyzing it. All right, thanks for watching this. See you in the next video. Thank you.